You flip a light switch, the room lights up. You never think about it. But right now, somewhere inside a concrete dam, that light is being powered by water making a 90-degree turn at close to 300 miles per hour. Not burning, not exploding, just turning. One smooth, continuous curve through a single spinning wheel. The machine making that happen is called a Francis turbine. You have probably never heard of it, but it generates roughly 60% of all hydroelectric power on Earth, more than any other turbine design ever built. And here's the surprising part. The reason it dominates is not raw power. It is geometry. Every curve, every angle, every taper inside that machine exists to control water so precisely that almost none of its energy is wasted. Today, we are breaking down exactly what happens inside a Francis turbine. After this, you will never think about a dam the same way again. Let's start with how the water gets in, because the engineering begins before anything even touches a blade. Water arrives from the reservoir through a massive pipe called a penstock. It is pressurized, fast, and carrying enormous energy. But you cannot just aim a fire hose at a turbine and expect it to work. The water needs to arrive at the runner from every direction at once, evenly distributed around the entire circumference. And it needs to arrive at the same speed and the same pressure no matter where it enters. That is the job of the spiral casing. Some people call it a volute. It looks exactly like a snail shell wrapped around the outside of the turbine. Water enters through one large opening, and the casing spirals inward, getting progressively narrower as it wraps around. Here is why. As the casing curves around the runner, water is constantly being drawn off into the turbine along the full circumference. That means the volume of water still traveling through the casing decreases the further it goes. If the casing stayed the same diameter all the way around, the water near the inlet would rush in with massive force, and the water at the far end would barely trickle through. Think about a garden soaker hose, the kind with tiny holes along its entire length. If the hose diameter never changed, the holes closest to the faucet would spray hard and the ones at the far end would drip. Taper the hose and every hole delivers equally. That is exactly what the spiral casing does. The decreasing cross-section compensates perfectly for the decreasing volume of water. The result is a uniform ring of energy feeding into the runner from every direction at nearly identical velocity and pressure, symmetrical, balanced, and absolutely critical for everything that happens next. Now the water is moving inward from the spiral casing in a nice uniform ring. But it is not ready for the runner yet, not even close. The flow is still swirling. It still has turbulence from the casing, and most importantly, it is not aimed correctly. Sending uncontrolled water into precision-shaped blades is like throwing a baseball with your eyes closed. The energy goes everywhere except where you need it. So before the water reaches the runner, it passes through two sets of structures that most people never think about. And honestly, these matter more than the blades themselves. The first set is called stay vanes. These are fixed. They do not move. They are welded directly into the structure of the turbine. Their job is straightforward, straighten the flow. The water coming out of the spiral casing still has a swirling component to it, a rotational momentum left over from traveling around that curved path. The stay vanes catch that swirl and redirect it, smoothing the flow and steering it inward toward the runner in clean, organized streams. They also serve as structural supports, physically holding the spiral casing together under enormous water pressure. The second set is where things get interesting. These are called guide vanes, sometimes called wicket gates. And unlike stay vanes, these move. Each guide vane can rotate on its own axis, opening wider or closing down, changing two things at once: the amount of water that gets through and the angle at which that water hits the runner blades. That angle is everything. The runner blades are shaped for a specific angle of attack. Water arriving at the wrong angle is like wind hitting a sail from the side. The energy transfer collapses. Guide vanes ensure the water always arrives at the optimum angle regardless of flow conditions. But here is the part that surprises most people. Guide vanes are also how a Francis turbine controls its power output. When the electrical grid needs more power, the vanes open wider. When demand drops, they close down. No speed change, no fuel adjustment, just geometry, adjusting in real time. Now, the water has been distributed evenly by the spiral casing, straightened by the stay vanes, and aimed precisely by the guide vanes. Everything up to this point has been preparation. This is where the actual work happens. The runner is the only moving part inside the entire turbine. It is a ring of complex-shaped blades mounted on a central hub, connected by a shaft directly to a generator. Water flows in, the runner spins, and that rotation becomes electricity. Simple in concept. But the way those blades extract energy from the water is anything but simple. Pick up one of those blades and look at it in cross-section near the inlet edge. You will see a thin, curved airfoil shape. The same basic profile you would find on an airplane wing. When water flows over that shape, it moves faster on one side than the other. Faster flow means lower pressure. The pressure difference between the two sides creates a force that pushes the blade sideways. That force is called lift. It is the same principle keeping a 747 in the air, except here it is not generating flight. It is spinning a turbine. Now look at the same blade near the outlet edge. The shape changes. It curves into something closer to a bucket. Water flowing along the blade hits that curve and changes direction sharply. That sudden change in momentum transfers force directly into the blade. A push, not a pull. That is an impulse force, the same kind of force you feel when you catch a heavy ball and your hands get pushed backward. Here's what makes the Francis turbine genuinely clever. It does not rely on just one of those forces. It uses both simultaneously. Lift from the airfoil shape pulls the blade through the water. Impulse from the bucket curve pushes it from behind. Two different energy extraction mechanisms working on the same blade at the same time. This is why a Francis turbine is not classified as a pure reaction turbine. A portion of the work comes from impulse action, and this dual extraction is one of the key reasons Francis turbines are so efficient. They are harvesting energy in two ways at once, squeezing the water from both sides of the physics. As the water passes over the blades, both its speed and its pressure drop. The runner is draining kinetic energy and pressure energy simultaneously. What enters as a fast, high-pressure stream leaves as slow, spent water with almost nothing left to give. Now here's the moment this whole video has been building toward. The 90-degree turn. Water enters the runner from the outside, moving inward toward the center, radially, like spokes pointing toward the hub of a wheel. But by the time that water leaves the runner, it is no longer moving inward. It is moving straight down, parallel to the shaft, axially. That is a complete 90-degree change in direction happening inside the runner at extraordinary speed. And here's what most people get wrong about that turn. It is not a problem the turbine has to deal with. It is the mechanism. That change in direction is the energy extraction. Think about it this way. When water changes direction, something has to supply the force to make that happen. In a Francis turbine, the thing supplying that force is the blade. The water pushes on the blade as it curves through that 90-degree path. And that push is what spins the runner. Every single degree of that turn represents momentum being transferred from the water into the machine. This is also why Francis turbines are called mixed flow turbines. The flow is not purely radial and not purely axial. It transitions from one to the other inside the runner itself. That transition is the entire point. The blade geometry manages this beautifully. The airfoil shape at the inlet handles the radial entry. The bucket curve at the outlet redirects the flow downward into the axial direction. The whole blade is one continuous, carefully calculated surface designed to guide the water through that turn as smoothly as possible. Too sharp, and the water separates from the blade surface. Too gentle, and energy passes through uncaptured. The curve has to be exact. Think of a highway off-ramp designed so precisely that a car at full speed can exit without ever touching the brakes. The geometry itself does the work. The water has made its turn, the runner has taken almost everything. But almost is not everything. And in engineering, what you do with the leftovers matters more than most people realize. Water leaving the runner is still moving. It is slow compared to what entered, but it still has velocity. And velocity is energy. If that water simply dumped straight out of the turbine into the river below, that remaining kinetic energy would be gone, wasted, thrown away at the exit door. That is where the draft tube comes in. It is the part of the turbine nobody talks about, and it is one of the most important components in the entire system. A draft tube is a gradually expanding channel fitted directly below the runner. As the water flows into this widening passage, it slows down. And when moving water slows down in an expanding space, something useful happens. The kinetic energy converts back into pressure energy. Velocity head becomes static head. That pressure recovery effectively lowers the pressure at the runner exit, which increases the total pressure difference across the runner itself. More pressure difference means more energy extracted from the same water. The draft tube is not just a drain pipe, it is giving the turbine a performance boost for free simply by managing what happens after the main event. But there is a catch. Low pressure at the runner exit is a double-edged sword. Drop the pressure too far and the water starts to vaporize, forming tiny bubbles that collapse violently against the blade surfaces. That is cavitation. Over time, it chews through solid steel like acid. The draft tube has to recover just enough pressure to boost efficiency without letting conditions cross that cavitation threshold. Get it right, and you gain free performance. Get it wrong, and you destroy the runner from the inside out. The margin is razor thin. Now let's put it all together. One unbroken sequence from start to finish. Water sits behind a dam. Gravity pulls it into a penstock. It accelerates. It enters the spiral casing, which wraps it around the turbine in a uniform ring, same speed, same pressure, every direction at once. Stay vanes catch the swirl and straighten it. Guide vanes aim it at the perfect angle and control how much gets through. The water hits the runner blades, where airfoil lift pulls and bucket impulse pushes simultaneously. The flow makes its 90-degree turn, entering radially, leaving axially, transferring momentum into the runner with every degree of that curve. The runner spins, the shaft turns, the generator produces electricity. Below, the draft tube catches the spent water, slows it down, recovers pressure, and sends it quietly into the river. Every component in that chain exists to prepare the water for the next one. The casing feeds the vanes. The vanes feed the blades feed the draft tube. Nothing works alone. Remove any single piece, and the whole system falls apart. And here is why Francis dominates. Other turbines are specialists. Pelton wheels need high heads and low flows. Kaplan turbines need low heads and high flows. Francis sits in the middle and performs at near peak efficiency across a broader range of conditions than either one. Different head heights, different flow rates, different dam sizes. Francis handles all of them. That versatility is not an accident. It is built into the geometry, and it is the reason 60% of the world's hydroelectric capacity runs through a Francis runner. There is no combustion inside a Francis turbine, no fuel injection, no exhaust, just water, geometry, and physics. A spiral casing that distributes evenly, vanes that aim precisely, blades that extract twice, a draft tube that recovers what others would waste. Every curve and every angle exists for one reason: to make sure that when water meets the runner, not a single joule is out of place. The real engineering here is not in the power of the water. Water has always been powerful. The real engineering is in the precision of the path. And now I am curious. Have you ever wondered what actually happens when cavitation goes wrong inside a turbine? What it sounds like, what it looks like, and how engineers fight back against water that is literally eating through solid steel? I've already started working on that one. Subscribe so you do not miss it.